Have you ever wondered how engineers can precisely predict the amplification of a common electronic circuit, especially one that flips the phase of its signal? Understanding this fundamental principle is key to designing countless devices, from audio equipment to control systems. The voltage gain of an inverting amplifier is derived directly from the application of Kirchhoff's current law at its inverting input terminal, combined with the ideal characteristics of an operational amplifier. This process elegantly shows that the gain is determined by the simple ratio of its feedback resistor to its input resistor, always resulting in a negative value that indicates a phase inversion. This derivation hinges on two crucial ideal operational amplifier assumptions. First, an ideal op-amp has infinite open-loop gain, which forces the voltage difference between its inverting and non-inverting inputs to be essentially zero. If the non-inverting input is grounded, the inverting input is therefore at a virtual ground potential. Second, an ideal op-amp has infinite input impedance, meaning that no current can flow into or out of its input terminals. These two characteristics simplify the circuit analysis immensely, allowing us to easily apply Kirchhoff's current law. To practically apply these concepts, you would first identify the current flowing from the input voltage source through the input resistor to the inverting terminal. Then, you would identify the current flowing from the inverting terminal through the feedback resistor to the output voltage. Because no current enters the op-amp's inverting terminal itself, these two currents must be equal in magnitude but opposite in direction. By setting up this equation and solving for the ratio of the output voltage to the input voltage, you arrive at the classic gain formula: negative R feedback divided by R input. This elegant derivation demonstrates why the inverting amplifier is such a versatile building block in analog circuit design. It offers a straightforward and reliable method to achieve a predictable voltage gain with phase inversion, using only passive components and an op-amp. The simplicity of controlling gain through mere resistor ratios highlights its practical utility in everything from simple signal buffering to complex filtering stages. Ultimately, the derivation of the inverting amplifier's voltage gain formula provides a powerful tool for predicting circuit behavior and designing precise amplification stages. By understanding the underlying ideal op-amp assumptions and applying fundamental circuit laws, you gain the ability to confidently manipulate signals and build functional electronic systems with predictable outcomes.